Hello everyone, my name is Naina and I am from the Bodhi Academy. Today we will continue with the chapter that is chemical bonding and molecular structure. In today's video, we will basically focus on two theories, VSEPR theory and VB theory, also known as VBT. Now what is VSEPR theory? VSEPR stands for valence shell electron pair repulsion theories, and VB theory means Valence Bond Theory or VBT. Let's start with the first theory, that is the VSEPR theory or valence shell electron pair repulsion theory. Now, as already explained in our previous videos, Levy's concept is unable to explain the shapes of molecule. So as I already told you, Levy's structure, it will basically tell you the number of valence electrons that are present or how many bonds are required by an atom to satisfy its needs, but it doesn't explain you anything with regards to the shape of the molecules. So this theory provides simple procedure to predict the shape of covalent molecules. So this theory was put forward to predict the shapes of the covalent molecule. As Levy's concept, it cannot explain the shapes of the molecule. Now, Sidgwick and Powell in 1940 proposed a simple theory based on the repulsive interaction of the electron pairs in the valence shell of the atoms. Okay, in 1940, Sidgwick and Powell, they just simply proposed a theory. Okay, a simple theory which was based on the repulsive interaction between the electron pairs in the valence shell of an atom. But it was further developed and refined by Nyholm and Gillespie. Okay, they further studied the concept and they redefined it. Okay, what are the main postulates of VSEPR theory, or what are the main things that VSEPR focuses on? So first one is the shape. The shape of a molecule depends upon the number of valence shell electrons, both bonded and non-bonded, around the central atom. So if there is a central atom, okay, so whatever electrons, valence shell electrons are there, whether they are paired or whether they are unpaired, okay, paired, that means bonded or non-bonded, okay, both around the central atom. So this determines the shape. Okay, the shape of the molecule, it depends basically on the bonded pairs and non-bonded pairs of electrons. Second one is pair of electrons in the valence shell repel one another since their electron cloud are negatively charged. Okay, so the pairs of electrons, okay, whatever present on the valence shell, they repel one another. Now because of this repulsion, there is a specific arrangement for the atoms around the central metal atom, and this repulsion is basically because of their electron cloud which are negatively charged. Okay, this pair of electrons tend to occupy such positions in space that minimize repulsion and thus maximize distance between them. So because of this repulsive features, the electron pairs which are there, they occupy such positions where they face minimum repulsion. Okay, so if they want to face minimum repulsion, they will distance themselves from each other. The distance will be maximum, so they will maximize the distance between them to minimize the repulsion. The valence shell is taken as a sphere with the electron pairs localizing on the spherical surface at maximum distance from one another. So the valence shell, okay, it is taken as a sphere with electron pairs localizing on the spherical surface at maximum distance from one another. So valence shell, it was considered to be a sphere, and in this sphere the electrons are localized far from each other. Okay, now a multiple bond is treated as if it is a single electron pair, and 2 or 3 electron pairs of a multiple bond are treated as a single super pair. Okay, a multiple bond, okay, when there is more than one bonds, that is your double and triple bond. In this case, your single bond is treated as a super bond, whereas your electron pairs with 2 or 3 electron pairs, for example your double and triple bond, okay, in this the extra bonds, okay, the double or the triple bond, they are called as single super pair. Each of them are called as single super pair. Where two or more resonance structures can represent a molecule, the VSEPR model is applicable to any structure. So it is not like when there is a resonance structure. I told you know what resonance structure is. So when there is a resonance structure, what is the basic difference between resonance structure? It is just the presence of the molecule from right to left, or the double bond. You can have a double bond on the right or on the left. So similar structure, they will have a similar chemical formula, similar energy, okay, only thing their arrangements will be different from each other. So in a resonance structure also you can apply the VSEPR theory, because there is no difference in the valence resonance structure, only the double bond is changing from left to right, okay. So the repulsive interaction of electron pairs decrease in order, okay. So there is a order for the electron pair decrease. So for lone pair, the repulsion is more, whereas lone pair, bond pair, the repulsion is compared to lone pair, bond pair has a less repulsive force, and bond pair has even less. So it goes like lone pair has more repulsion between them. After lone pair, there will be lone pair, bond pair, and least repulsion is observed between bond pair and bond pair, okay. So Nylom and Gillespie refined the VSEPR model by explaining the important difference between the lone pairs and bonding pairs of electrons. So what they did, Nylom and Gillespie, they refined the VSEPR theory. Refined means they redesigned the VSEPR theory by explaining the important difference between lone pairs and bond pairs. Now, as I told you, there are lone pairs and bond pairs. So Nylom and Gillespie, they simply differentiated between lone pairs and bond pairs of electrons. Now, while the lone pairs are localized on the central atom, each bonded pair is shared between two atoms. Now, what is the difference between lone pairs and bond pairs? For example, if I take water, okay, oxygen, you have two bond pairs with hydrogen, oxygen hydrogen bonded pairs, and there are two pairs of unpaired electrons which are present on the oxygen, okay. So these unpaired electrons are called lone pairs, okay. So lone pairs, they are localized on central metal atom. Localized on central metal atom means they are involved with central metal atom only, okay. So they are the part of central metal atom. They will occupy more space compared to the bonding pairs, okay. In bonding pairs, the electrons are shared, whereas the lone pair electrons are entirely for your central metal atom, or for that matter whichever atom that lone pair is present on. So this lone pair will occupy more space compared to the bonded pairs of electrons. Now this results in great repulsion between lone pairs of electron as compared to the lone pair bond pair and bond pair repulsion. So here what will happen, there will be more repulsion between this lone pairs, because both are negatively charged. As you know, like charges, they will repel each other. So these lone pairs will highly repulse each other, since because of their repulsion there is lone pair bond pair repulsion which is taking place. Hence the structure of water, as I already told you, water according to its chemical formula it should have a linear structure, but because of the presence of these lone pairs there is more repulsion between the lone pairs, which pushes the hydrogen downwards, so that the lone pairs can adjust themselves, arrange themselves in such a way that the repulsion between them decreases, okay. Hence the water gets its standard bent structure, okay. This repulsion effect results in deviation from idealized shape and alteration in bond angles in molecules, as I told you. So the idealized shape for water molecule is a linear shape, but because of this lone pairs there is high repulsion, and that repulsion causes the pushes the hydrogen downwards, hence changing the bond angles and alterations to the idealized shape. For prediction of geometric shapes of molecules with the help of VSEPR theory, it is convenient to divide molecule into two categories. Okay, so to predict a geometrical shape, okay, using VSEPR theory, it is convenient if we divide the molecule into two categories. First is molecule in which the central atom has no lone pairs, and molecule in which the central metal atom has one or more lone pairs. So to conveniently arrange or understand the shapes of a molecule, geometrical shapes of a molecule using VSEPR theory, it is better we divide the molecules into two categories. First category will have molecules with no lone pairs on the central atom. There won't be any lone pair on the central metal atom or central atom. And second category will be the molecules which has central atom with one or more lone pairs associated with it. Now the arrangement and pairs about a central metal atom A without any lone pairs and geometries of some molecules ions of that type. So here in the following tables it is given, so I'll explain them. So there are both the ones with lone pairs and the ones without lone pairs also given here, as depicted in the compound of AB2, AB3, AB4, AB5 and AB6. B atom around the central atom A are linear, trigonal, tetrahedral, diagonal, bipyramidal and octahedral respectively. So here there is an example. So this is AB2. Okay, AB2, AB3, AB4, AB5 and AB6. Okay, so here AB2, A is your central atom and B is the one which are associated with it. So mostly AB2 it forms a linear structure. For example, BCl2, HgCl2. Okay. AB3 is the molecule. You have to add another another molecule to the central atom. Okay, and it forms a trigonal planar structure. Then AB4 with 4 molecules associated with the central atom, it gets a tetrahedral structure. When there is 5 molecules associated with the central atom, it becomes trigonal bipyramidal. And last shape is the octahedral when 6 molecules are associated with the central atom. Now all these shapes are formed because there is no lone pairs that are associated with these molecules. Okay, if there is no lone pair which are associated, then you will get this kind of arrangements when there is the molecules with formula like AB2, AB3, AB4 and AB6. Now, the VSEPR theory is able to predict geometry of a large number of molecules, especially the compounds of p-block elements accurately. Now, using VSEPR theory, large number of molecules have been predicted with their geometry, okay, as mostly the compounds which are related to p-block elements. Their geometrical shapes are predicted accurately. Now it is also quite successful in determining the geometry quite accurately even when the energy difference between possible structures is very small. So by using VSEPR theory, they have successfully determined the geometry of the molecules where the energy difference is very low. The energy is almost same. Okay. Now the theoretical basis of VSEPR theory regarding the effects of electron pair repulsion on molecular shapes is not clear and continues to be a subject of doubt and discussion. So the theoretical basis, okay. Theoretically, the VSEPR theory regarding the effects of electron pair repulsions on molecular shapes is not clear it has not been explained properly. So it is still a subject of doubt and discussion. There are still works which are going on the VSEPR theory. Now, what if you have a electron pair or lone pair associated with a molecule? Now, this above table here, all the molecules, they have a linear, trigonal, planar, tetrahedral, trigonal, bipyramidal, octahedral structures, because there is no lone pair that is associated with it. But what if there is a lone pair associated? What type of structure will it give you? So when there is a AB2 structure, without a lone pair it will form a linear structure, but when there is a lone pair associated with it, it will always give you a bent structure. Basic example is your SO2O3. Next is AB3E. AB3E means you have a AB3. It will give you a trigonal planar structure without electron pair or lone pairs. But what if there is a lone pair? When there is a lone pair, it will give you a tetrahedral or a trigonal pyramidal structure. Okay, there will be a triangle and a pyramid which is formed. Okay, when you have two bonded pairs and two lone pairs associated to it, for example is your water. Water has two lone pairs associated with it. In this case also you have a bent structure. Okay, now AB4 with the electron pair, you will get a seesaw structure. See, these bonded pairs, you get a seesaw structure. So these are the structures when there is lone pairs associated to it. Now why they are associated? Reason is given here. It is basically because of the repulsion between the lone pairs, which pushes the bond pairs downwards, so that the repulsion between the lone pair is minimized. Okay. Now next is the valence bond theory. Next theory is VBT or valence bond theory. As we know that Lewis approach helps in writing the structure of molecules, but it fails to explain the formation of chemical bonds. Using Lewis approach, you can write the structure, but it doesn't explain you exactly the formation of chemical bonds, how chemical bonds are formed. It just says because there are electrons available, you can pair up the atoms, but what exactly happens when the atoms are paired up? So it also does not give any reason for the difference in bond dissociation enthalpy and bond lengths in molecules like hydrogen and fluorine. So it doesn't give any reason, okay, for difference. Why the dissociation enthalpy of hydrogen and fluorine varies? Why there is a difference between their bond lengths and the dissociation enthalpies? So although in both the cases single covalent bond is formed by sharing of an electron pair between the respective atoms, even though both the atoms, hydrogen and fluorine, in both cases there is a single covalent bond which is formed by sharing of an electron pair between the respective atom, still their bond length differs, the dissociation enthalpy, bond dissociation enthalpy, that is the energy required to break the bond, also differs. Now why it differs? That also Lewis approach can't explain. So it also gives no idea about the shapes of polyatomic molecules. Again here, Lewis approach, as I told you initially, it doesn't give you anything to do with the shapes. Now, similarly, the VSEPR theory gives the geometry of simple molecules, but theoretically it does not explain them, and also it has a limited application. So VSEPR theory, just now we have seen, even though it explains the geometry of simple molecules, but as I told you, theoretically it is still in doubt and discussion, and also its application is limited. So to overcome these limitations, the two important theories based on quantum mechanical principles are introduced. So to overcome all these queries or to answer all these questions, two mechanical principles were introduced based on the quantum mechanical principles. These are your VB theory, that is valence bond theory, or VPT, or MO theory, that is molecular orbital theory, or MOT. So let's see what valence bond theory is. Now, valence bond theory was introduced by Hitler and London in 1927 and developed further by Pauling and others. Similarly, this valence bond theory, it was put forth or introduced by Hitler and London, and later it was developed by Pauling and others. Now, a discussion of valence bond theory is based on the knowledge of atomic orbitals, electronic configuration of elements, the overlap criteria of atomic orbitals, the hybridization of atomic orbitals, and the principles of variation and superpositions. Now, on what basis or on what topic does the valence bond theory is discussed? So valence bond theory, it is basically based on the knowledge of atomic orbitals, electronic configuration of the elements, the overlap criteria of atomic orbitals, how they are overlapping or how the bond is formed, and the hybridization of atoms, okay, atomic orbitals, also with the principal variation and superpositions. Now, a rigorous treatment of the valence bond theory in terms of this aspects is beyond the scope of this book. So all this criteria to explain in detail what valence bond theory is out of this book, because it is lot of things is there to explain if we go in detail to learn the valence bond theory. Therefore, for the sake of convenience, in this topic we will be only discussing the terms qualitative and non-mechanical treatment only, non-mathematical treatment only. Okay. We will just roughly define the term non-mathematically what valence bond theory is and how exactly it operates, and some terms involved in valence bond theory. Because if we want to do a deep study on valence bond theory, it will go a long way, and so for the convenience we will restrict it to the rough introduction part of the valence bond theory. Now, to start with, let us consider the formation of hydrogen molecule, which is the simplest of all molecules. So here the valence bond theory has been explained to you all with respect to hydrogen molecule. Now consider two hydrogen atoms, A and B. Now hydrogen molecule, you know, it is H2. So consider both the hydrogen molecules as A and B. Okay, both the hydrogen molecules, one of them as A, another one as B. Now, approaching each other having a nuclei Na and Nb. Consider both of them having a nucleus Na and Nb. N stands for nuclei. Okay, having a nuclei of Na and Nb. And the electrons present around them are represented by Ea and Eb. Since hydrogen, the atomic number is 1, both the hydrogens will have 1 electrons around them. So Ea and Eb is fine for their representation. So when the two atoms are at a large distance from each other, there is no interaction between them. So it's something similar to your magnet. When we keep them at a long distance, okay, there won't be any interaction between both of them, right? So as these two atoms start approaching to each other, when they are far apart, they won't interact with each other. But as they start coming closer and closer to each other, okay, there is an attractive and a repulsive force which begin to operate. Okay, some of them will attract, some of them will repel. So there is an attractive and a repulsive force that begin to operate between them. Now, what are the attractive forces that arise between them? Now, the attractive force that arise between them are basically the nucleus of one atom and electron of its own atom. So there can be an attraction between nucleus and electron of the same atoms. Okay, since nucleus has protons associated with it, it will be positive in nature, and electrons basically it are negative in nature. So positive, negative, they will attract each other. Okay, second will be the nucleus of one atom and electron of other atom. So there are two attractive forces that takes place. First is the nucleus and the electron are from the same atom. Second, the nucleus from one atom and the electron will be from other atom. Okay, So these are the two attractive forces that takes place. And similarly, you will have a repulsive force that arises. Now what are the repulsive force? Repulsive force will be basically between the electrons, both the electrons and both the nucleus. Since electrons are negatively charged, since they are like charges, they will repel each other. Nuclei being they have protons with them, so they are positively charged. So being positively charged, they will repel each other. So the nucleus of both the atom will repel each other, and the electrons of both the atoms will repel each other. Okay, so these are the attractive and repulsive forces that takes place. Now the attractive forces tend to bring the two atoms close to each other, whereas repulsive forces tend to push them apart. This there is no need to explain. You know, attractive forces will bring them together, whereas repulsive forces will push them apart. Okay, so this is the attractive force that takes place. Okay, electron, EB, and this is the nucleus. Okay, so there is an attractive force that takes place, and there is a repulsive force that takes place. Now, experimentally, it has been found that the magnitude of new attractive force is more than the new repulsive force. So these are the old repulsive force. Old repulsive forces, old attractive forces. Old attractive forces means the attractive forces between the nucleus and the electron of the same atom. Because before both the atoms come closer to each other, they are separately arranged, right? So they are present in themselves. So in that case, they will be attracted towards each other. Like the nucleus and the electron of the same atom, they will be attracted towards each other. Here you can see this is the nucleus of atom A and this is the electron of atom A. So they will be attracted towards each other. But when these molecules start coming, when both the molecules start coming to each other, there will be an attractive force between the nucleus of A and the electron of B. Okay, so these are the new forces that are generated. So the new forces, new attractive force which are formed are more than the new repulsive forces which are generated. So as a result, two atoms approach each other and potential energy decreases. Since the energy of repulsion is less than the energy of attraction that is generated, as a result of that, both the atoms they approach each other. Okay, and the potential energy overall it decreases. So ultimately, a stage is reached where the net force of attraction balances the force of repulsion and system acquires a minimum energy. So once both the forces they complement each other, the overall force balances. So there is equal amount of attraction and equal amount of repulsion, which acquires minimum energy and the molecule is stabilized. At this stage, two hydrogen atoms are said to be bonded. Okay, so when they reach to a point where their energies are stable, there is equal repulsion and equal attraction between them, and the molecule is stable. At that time, it is said that there is a bond which is formed between both the hydrogen atoms. So together to form a stable molecule having the bond length of 74 picometers. So once we say the hydrogen is bonded, it forms a bond length of 74 picometers. Now, since the energy gets released when the bond is formed between two hydrogen atoms, the hydrogen molecule is more stable than that of isolated atoms. So when the both of the hydrogen atoms, when they combine and form a bond, okay, there is energy which is released, and this release of energy makes the hydrogen molecule more stable than the isolated hydrogen atoms. Okay, so the energy so released is called bond enthalpy. Okay, so the energy which is released during the formation of bond is called bond enthalpy, which is corresponding to minimum in the curve. So conversely, 435.8 kilojoules of energy is required to dissociate 1 mole of hydrogen molecule. So this is the energy which is required to separate both of the hydrogen molecules. What is orbital overlapping? So in the formation of hydrogen molecules, there is a minimum energy state when two hydrogen atoms are so near that their atomic orbitals undergo partial interpenetration. So here you can see both the hydrogen atoms, they start coming closer to each other. At a point, there is a point where both the hydrogen atoms are so close that they start to penetrate into each other. They start to go inside each other. Okay, now this partial merging of atomic orbitals is called overlapping of atomic orbitals, which results in the pairing of electrons. So this partial merging of atoms, okay, this partial merging of atoms, this is said to be the overlapping of atomic orbitals, and this overlapping gives rise to the pairing of electrons. Now the extent of overlap decides the strength of a covalent bond. Okay, to at what extent the overlap has taken place, to what extent the overlapping has done, that results in the strength of the covalent bond. If the overlapping is more, the strength is more. So in general, greater the overlapping, stronger is the bond formed between two atoms. So how great the overlapping is, that stronger the bond is. So therefore, according to orbital overlap concept, the formation of a covalent bond between two atoms results by pairing of electrons present in the valence shell having opposite spins. For example, opposite spins means if I lock my hands in opposite directions, this is more stronger than overlapping them like this. So when they are in opposite spins means these are opposite spins. So once they lock each other, it is difficult to remove them. Okay, so the electrons or valence electrons should have an opposite spins. Next is directional properties. Here one more thing you have to remember, more the overlapping, stronger the bond. That is the main concept for orbital overlapping concept. So directional properties of bonds. As we have already seen, the covalent bond is formed by overlapping of atomic orbitals. So the molecule of hydrogen is formed due to the overlap of 1s orbitals of two hydrogen atoms. Now the covalent bond which is formed, okay, it is formed by overlapping of atomic orbitals. Now the molecule of hydrogen which is formed is due to the overlap of 1s orbital, because hydrogen has only 1s orbitals. So overlapping of this 1s orbitals form the hydrogen atoms. In case of polyatomic molecules like CH4, NH3, H2O, the geometry of the molecule is also important in addition to the bond formation. This is the homoatomic molecules. Both are hydrogens. When there is a polyatomic or heteroatomic molecules like CH4, NH3, H2O, the geometry of the molecule is also important in addition to the bond formation. For example, why is it so that CH4 molecule has a tetrahedral shape and HCH bond angles are 9.5 degree? Why is the shape of the NH3 molecule pyramidal? So to understand these concepts, you should know the geometry of the molecule. So the valence bond theory explains the shape, the formation and directional properties of the bond in polyatomic molecules like CH4, NH3, H2O. So valence bond theory, it basically explains the shape, formation and directional properties of the bonds. So in terms of overlap and hybridization of atomic orbitals. So on what basis they explain? They explain it in terms of overlap and hybridization of atomic orbitals. Now overlapping of atomic orbitals. So when orbitals of two atoms come close to form a bond, their overlap may be positive, negative or zero depending upon the sign and direction of orientation of amplitude of orbital wave function in space. So when two orbitals, okay, when orbitals of two atoms, when they come closer, they can form an overlap with positive, negative and or zero. depending upon the sign and direction of orientation of their amplitude, direction of their orientation, in what direction they are arranged. Now, positive and negative signs on boundary surface diagrams shows the sign phase of orbital wave function and are not related to charges. These signs are basically there to show the lobes. Okay, it doesn't have anything to do with the charge of the molecule. So orbitals forming bond should have same sign and orientation in space. So it is basically the orbitals, okay, which form the bond. It should have same sign, I'll explain that thing, same sign and orientation in space. Okay, so it has nothing to do with the charge. This is called positive overlap. Various overlaps of s and p orbitals are depicted. So when you have an overlap, okay, with an orbit having same sign and orientation in space, this is called positive overlap. Now, the criteria of overlap as the main factor for the formation of covalent bond applies uniformly to the homonuclear, heteronuclear, diatomic molecules and polyatomic molecules. So the criteria of overlapping, it is uniform for all the molecules, whether it is a homonuclear, heteronuclear, diatomic molecules or polyatomic molecules. We know that the shapes of CH3, NH3 and H2O molecules are tetrahedral, pyramidal and bent respectively. Okay, so CH4 has a tetrahedral structure, NH3 has pyramidal and H2O has a bent structure respectively. Now it would be therefore interesting to use VB theory to find out if these geometrical shapes can be explained in terms of the orbital overlaps. Okay, so valence bond theory, it is used to find the geometrical shapes and can be explained in terms of their orbital overlaps. So let us first consider the CH3, that is methane molecule. Now, the electronic configuration of carbon in its ground state is, so carbon electronic configuration will be 1s2, 2s2, 2p2 because its atomic number is 6. So here we will consider methane, CH4. Okay, this is the ground state electronic configuration. When it goes to excited state, what happens is 1s2 will remain there same, 2s2, 2px, 2py and 2pz. You know p orbital has 3 columns into it, x, y and z. Okay, so the electrons in 2p are 2, so 1 and 2, each electrons in x and y. Okay, from 2s orbital, 1 electron is transferred to 2pz. Okay, so now we have 4 unpaired electrons present in carbon, 2s1, 2p3. Okay, each of the p orbital has 1 unpaired electrons in them. The energy required for this excitation is compensated by the release of energy due to overlap between the orbitals of the carbon. So when carbon-carbon overlaps, okay, when carbon overlaps with any of the molecule, at that time whatever energy is taken, okay, that energy compensates for the energy required to transfer this 1 electron from s orbital to p orbital. We are shifting 1 electron from 2s orbital to 2p orbital, no? So the energy which is required to excite or transfer these electrons, that energy is compensated when the orbitals are overlapped between carbon and hydrogen. Now the 4 atomic orbitals of carbon, each with an unpaired electron, can overlap with 1s orbitals of 4 hydrogen atoms which are also singly occupied. So here what will happen? We have 4 unpaired electrons in carbon molecule, excited carbon atom. right? When carbon is in excited form, we have 4 unpaired electrons present in that carbon, 1 in the 2s orbital and 3 in the p orbitals. Now each of these unpaired electrons, what they do is they take up 1 electrons from the hydrogen atom and satisfy or completes the electron pair. So each of the electrons will be taken from the hydrogen atom. So since there are 4 unpaired electrons, 4 hydrogen atoms are used, okay, to overlap. So positive overlap means the overlapping takes place between the similar orbitals. Both the positive orbitals, when the overlapping take place in both positive orbitals or the orbitals with same signs. Here you can see positive, positive, negative, negative. So when the overlapping is between same charged lobes, it is called as positive overlap. And when the overlapping is between two different signed lobes, positive, negative, okay, when there is overlapping between two different sized lobes, it is called as negative overlapping. Zero overlap means they will overlap with both, either with both, or they won't overlap at all, okay. So these are zero overlap. Now hence methane, when you have 4 electrons unpaired, you take 4 hydrogen, each hydrogen has 1 electrons to it. What they will do, they will pair up and satisfy both the molecules. Hydrogen is also satisfied, carbon is also satisfied, and they forms 4 CH bonds. Now it will however be observed that while the 3 p orbitals of carbon are at 90 degree to one another, the HCH angle for this will also be 90 degree. So the p orbitals, they are arranged in 90 degree to the on carbon. The lobes are arranged in a 90 degree format, okay. That's why the structure of methane is like this. The angle is 90 degree for all the CH bonds. Now that is 3 CH bonds will be oriented at 90 degree to one another. The 2s orbital of carbon and 1s orbital are spherical, symmetrical, and they can overlap in any direction. So p orbitals, they will be arranged in 90 degree, and the s orbitals, both are s orbitals. So they, and both are spherical in shape, so they can orient in any direction. And therefore the direction of the 4th CH bond cannot be ascertained. So the rest 3 you can say that they are present 90 degree to the carbon, but the 4th bond you cannot predict at what angle it will be present, because both are symmetrical in shape. This description does not fit in with the tetrahedral HCH angle 109.5 degree. Clearly, it follows that simple atomic orbital overlap do not account for the directional characteristics of bonds in CH3. So here you cannot predict the bond angle of HCH as 109.5 degree, because you cannot predict the bond angle of the third, or cannot predict the bond, 4th bond, where it will be formed. So here it clearly says that simple atomic orbitals, when they overlap, they doesn't play any role in the directional characteristics of the bond. So using simple procedures and arguments, it can be seen that the case in NH3 and H2O molecules and angles about should be 90 degree. This is in disagreement with the actual bond angles of 107 and 104.5 degree in NH3 and H2O molecules respectively. So on this basis, if we go with further examples like NH3 and H2O, it should also follow the same pattern of 90 degree bond angle, but there is a disagreement. It is not seen to have a 90 degree bond angle, because you know water has the bond angle of 104.5 degree. types of overlapping and nature of covalent bonds. What types of overlapping are there? Now the covalent bond may be classified into two types depending upon the types of overlapping. Okay, so covalent bond, they are classified into two types depending upon their overlapping: sigma bonds and pi bonds. Now what are sigma bonds? Sigma bond, this type of covalent bond is formed by the end-to-end or head-on overlap of bonding orbitals along the internuclear axis. This is called as head-on overlap or axial overlap. This can be formed by any of the following types of combination of atomic orbitals. Now what is sigma bonds? This is a type of covalent bond which is formed by the end-to-end or head-on overlap of bonding orbitals along the internuclear axis. Along the axis, so this, along the axis, head-on overlap. Both the heads, they overlap together. This is what sigma bond is. Okay. This is called as head-on overlap or axial overlap. This can be formed by any of the following types of combination. For example, SS overlap, SP overlapping, PP overlapping. Okay, all these three overlapping can be seen in sigma bonds. In case of SS or overlapping, there is overlap of two half-filled s orbitals along the internuclear axis. So you will have two s orbitals which overlap with each other to form SS overlapping. This also gives rise to a sigma bond. Okay, now next you have sp overlapping. Sp overlapping means there will be an half-filled s orbital and one of the atom and half-filled p orbital of another atom. So we will have two orbitals, s and p, both are half-filled. So this is sp overlapping. Then you have pp overlapping. Now this type of overlapping takes place when you have half-filled p orbitals of the two approaching atoms. When there are two different approaching atoms, both are having half-filled p orbitals, then they overlap to form pp overlapping. In all these three conditions, sigma bonds are formed. Sorry. So next one is your pi bond. Now, in the formation of pi bond, the atomic orbitals overlap in such a way that their axes remain parallel to each other and perpendicular to the internuclear axis. So whenever there is a pi bond formation, the orbital overlapping takes place in such a way that the axes remain parallel to each other. For example, here, the axis, it remains parallel to both of them. Okay, when it remains parallel to both and perpendicular to the internuclear axis. Now the orbitals formed due to sidewise overlapping consist of two saucer type charged clouds above and below the plane of the participating atoms. So this is how the pi bonds are formed. So here you can have double bonds. See, there are two bonds which are formed with the linear line perpendicular to the internuclear axis. Now, what is the strength of sigma and pi bonds? Basically, the strength of bonds depend upon the extent of overlapping. This I already told you when we were discussing the overlapping concept, that the strength of the bond, it depends on the extent of overlapping, to what extent the overlapping has taken place. In case of sigma bonds, the overlapping of orbitals takes place to a larger extent. Okay, sigma bonds, the overlapping is more. So hence it is stronger as compared to the pi bonds, where the extent of overlapping occurs to a smaller extent. So compared to sigma and pi bond, sigma bond is more stronger because it has a greater extent to overlapping. It has more overlapping seen in them compared to the pi bonds. Further, it is important to note that in the formation of multiple bonds between two atoms of a molecule, pi bond is formed in addition to a sigma bond. So when there is a multiple bond formation, okay, a pi bond is additionally formed along with an sigma bond. Okay, there will be a sigma bond and the second bond will be a pi bond. And if we want to break the bonds, pi bond will break first. Okay, so in today's video we have seen the overlapping, types of overlapping. Basically what we have started is with the theories, that is valence bond theory and VSEPR theory. In valence bond theory we have learned about orbital overlapping, directional properties and types of overlapping and nature of the covalent bond. So thank you for watching my video. Please do like, share and subscribe to our channel.